Welcome, welcome. We're in page 7 of the apportionment notes, and in this video we're going to talk about something called the population paradox. This is when the population increases in some states over the course of a period of time, and between those two population differences, you run the apportionment method, and there's an issue wherein a state whose population increased like at a faster rate than a different state still ended up losing a seat to that other state. So we have this example fully drawn out, and let's see what happens. An important note is that we're going to use Hamilton's method. And then the summary information that you should keep track of is we have 5 states. We started with 9 million people, and at the time of the next kind of like population count census, we had 90,000 more people. So let's take apart the table. So the columns list the different states changing, and each section is a different population. So we can see that A didn't change in population, B didn't change in population, C did change in population, so let's somehow make a note of that. C's population increased. D's population did not change. E's population did increase. So only 2 states changed in population, and the change in E was 10,000, while the change in C looks like about 80,000. Let's see what else changed. Well, the standard quotas all changed, it's looking like. So 8.3 to 8.25, 4.33 to 4.29. And this makes sense that the standard quotas are changing for all the states, even though the populations are not changing for all the states, because the standard divisor is changing. And remember that the standard divisor is the total population divided by the total number of seats that are being distributed. So that changes when the population changes. So each one of these populations is being divided by a different number. And so that's why the standard quota can change even though the population can stay the same. So that's something to keep note of. And then lastly, let's check to see where the apportionment changed. So that like what material change was there for the people living in the states. So in A, they had 8 seats in both situations, so nothing happened. B, however, did change. They gained a seat. And remember, there's only 50 seats total. So if B gained a seat, somebody must have lost a seat somewhere. C, whose population went up by 80,000, didn't change. D's population stayed the same. Their apportionment stayed the same. And so E must be where it's happening. E's apportionment has gone down. So that's the paradox here. That's the issue here. That's what's going to make E upset. B's population didn't change. It stayed the same. But they gained a seat. E's population increased. But they lost a seat. And, their population maybe didn't go up by that much, only 10,000. But compared to not going up at all, that's a lot. And so this is the issue. This is why E is not going to be in favor of Hamilton's apportionment method. This is a critique of Hamilton's apportionment method, because only Hamilton's suffers from this. And it doesn't happen all the time. It just can happen. A method of the ones that we've studied can suffer from this. the divisor methods don't. And again, the divisor methods are Jefferson's, Adams, Webster's, and Huntington Hill. So that's the population paradox, and we have another hit against Hamilton's method with this. In the next video, we'll discuss the last paradox. See you there.